Hello, everyone that is here. Thank you for coming to listen to me speak to you. So we have Back to Basics, or in this version is Intro to ICS Cybersecurity, anything but basic. See what I did with the words there? So this is to be considered an introduction into industrial control systems and some of the mindset of security that would go behind it. If you want the part 2 or deeper dive, you will all drop everything and go to Cyber Warrior Con tomorrow in Fayetteville. Or not, that's fine too. So by me, Mike Curnow. A little bit about who I am, why I'm here. So I have kind of got my start in doing freelance web design, ended up picking up a few contracts, did more back-end development, just a bunch of PHP stuff. So things like WordPress, Magento, Expression Engine, stuff like that. Then I started working for a financing software firm as a software integration engineer. So basically writing the API codes that allowed systems to talk to systems, whether it be from the e-commerce side, and then kind of ingesting that and spitting out meaningful things for the APIs of a lending bank or something, right? I founded a consulting firm, had that for about a year, ended up getting busy with life. So from there, it just we dissolved the LLC. For 3 years, I was a programming and cybersecurity instructor for the Coder School in Cary, which is on Davis Drive, but it's literally the other end of it, going towards Apex. So I did that for a few years. I was the head of security services for an international MSP for a few years too. So what I do right now, I'm the lead security operations center architect for a cybersecurity firm out of Detroit, Michigan called Black River Cybersecurity. We are a cyber-physical security firm with a firm foothold in the automotive space. So like all the smart cars and connected cars out there, we do a lot of testing of the things that go into those. The chief information officer for a financial tech predictive analytics firm called RapidCat. It's based out of Raleigh, North Carolina. It's a predictive analysis platform, uses machine learning and neural nets to help those who play in the Forex binary market. And then I'm a public speaker, so occasionally I speak in public, like the store or here at the gas station. So part of my, expertise and skill set is really in cybersecurity. It's architecting and engineering security operations centers. So whether it be the tools, the people, the procedure, or just engineering a SIEM from scratch, typically based off of Elasticsearch or whatever other kind of flat file indexing system that you'd want to use. And then in cyber-physical system security, cyber-physical systems, for those of you who don't know, it's essentially whenever a cyber action has a physical reaction. So you can think smart cars, IoT that interfaces with real physical world, a lot of industrial manufacturing equipment, all industrial manufacturing equipment, I should correct myself. So in those, my specialties are industrial control systems and securing industrial control system infrastructures for IT/OT convergence, which is the connectivity between closed-off physical operational networks to things like cloud-based analytics and stuff like that. So piping data up to the cloud, but doing it securely without exposing your industrial assets, making them ripe for attack. So getting into it here, industrial control systems is a general term that covers anything that's on a factory floor. So it could be SCADA systems, it could be DCS or distributed control systems, which I'll get into a little bit more later. PLCs or programmable logic controllers. They're all found in industrial sectors, so water, oil, gas, electrical. So here we have an escalator, we've got a street light, we've got a power lines indicative of power grid, we have power plant, and we have a streetcar. Can anyone hazard a guess of what all of these have in common?
Industrial control systems.
They're very good. They're industrial control systems, okay? Or they contain industrial control systems. That's really good. It's like you almost knew it was coming next. Industrial control systems is what they have.
I promise I've not seen this before.
So, yeah, I've talked on this a little bit, and I try and tweak and add new things each time. So, but yeah, you might have seen this before. So where are they? Streetlights, water treatment facilities, solar farms, like photovoltaic control systems or ICS. They're all mostly Modbus controllers. The oil industry, production lines, power grids and plants, transportation, like automated transportation, and OMG, like literally tons of places. A little bit in kind of how it's used. There's you can have a single purpose setup to where a PLC, you have the HMI, which is just a computer that gives you output from a PLC. You have a PLC, which is a programmable logic controller. It's essentially a small ruggedized computer that controls a single physical service, right? So all's good, nothing happened. So I'm gonna pass this around. You can take that phone. So what I'm passing around is a teeny tiny controller that's on a rail that has input output. It's got Ethernet input. It's got a DC power adapter port. That's just for people that haven't seen what a controller might look like. They're not all going to look like that. That's just a small thing. It's not expensive like a Siemens or a GE piece of hardware. So yeah, as I was saying, you can have a single purpose, which is where you have a PLC doing a single function, single purpose, which is an escalator. Funny thing about escalators, if it breaks, it becomes stairs. That's Mitch Hedberg, rest in peace. Yeah. Then we have a distributed system. Distributed system, or distributed control system, is we have multiple control devices that are controlling multiple pieces of equipment, right? So often in unison or in orchestration of something else. And then when we get into here, going a little bit deeper, we have the Purdue Model. So this right here is called the Purdue Model. It used to be how things were actually networked and set up. So you can see right here, we've got all our sensors, actuators, all that kind of stuff, pumps, whatever have you, at the bottom layer. And as you go up, you're increasing in this control hierarchy. So that might seem somewhat familiar to people who've worked in networking for a while. You might not have worked in this specifically, but the idea should make sense. And it used to be the way that things were set up 100% all the time, because all these devices, it was all serialized, right? There was no Ethernet, there was no fiber, none of that stuff. Now it's a bit more of a notional networking architecture that acts as a guideline. So if you want to set up control systems for whatever control purposes you need, you would work with, you would start from the Purdue model and then work down. And some people say it's dead, but they're talking about the literal sense. But as a guidance on networking architecture, it's very much alive. To make it a little bit more simple to grab here, business planning and logistics, that's all stuff that will exist on your, actually, you know what, I skipped a whole part here. So pretty much right here, this separation, that's your IT networks, that's your enterprise networks, right? And so we have the DMZ right here, and then from here, from your respective firewalls, you're segmenting this here, and so you have the OT network, or the operational technology network, which all the industrial control systems will reside. And then up here you have your enterprise network that's got your, I don't know, your printers, your computers, your workstations, anything else that connect to the internet, like Xbox or whatever, if your office lets you have that stuff. So next, yeah, just kind of making it a little bit more simplistic. Level 4 is always going to be separated. That's segmented from the network. That's a whole separate thing. That's never going to touch the ICS network. And the reason for that is you never want to have a flat network, because typically whenever industrial system event happens, that's a bad thing. It typically finds its way from the IT infrastructure, and more often than not, that's from a flat network where you don't segment them properly. So then you have the manufacturing operations and control, which is the top of the hierarchy of the separated network for the OT side, and just goes down from there. Just a little bit of a higher level of the original picture. So I give this example of the Klondike Bar Factory, and I will say what I say to everybody else before I talk about this. If any of you out there have actually been to the Klondike Bar Factory and you want to tell me that this is not how they make Klondike bars, I don't want to hear it. Okay, we're just gonna go with this. This is at least in my head how I imagine they might do it. So you have, as we went through earlier, a few slides ago, we have processes, right? So you might have this here might be a mixer to mix the stuff that makes the Klondike bar, the ice cream, the chocolate, whatever. Then you have a refrigeration action, right? So like you're freezing this to make ice cream. And then you're putting it into squares. It's the best way to put it. Fashioning it into what will then be wrapped and then shipped out. Thank you, sir. And so for each of these processes, you're going to have a controller or a PLC, and that's going to dictate the actions on these different physical functions, right? And so then we'd have our HMIs, which you don't necessarily need an HMI at this level. Typically, if you're on a plant floor or anywhere that's exercising industrial control systems in their network and employing them in their network somewhere, you'll have a HMI or a human machine interface. Typically, it comes in the form of a touch screen on a cabinet somewhere, or it's a web GUI. Typically, PLCs might have a web GUI that you can just log into. Best practice is just turn those off for reasons. So when the PLCs will then tell the physical hardware to do a thing. Then once that thing's done, it will then tell next PLC, hey, next PLC, I'm done. Let's continue this process, and it continues on the chain, right? And it continues all the way till the end, and then we have Klondike bars. However, if something were to go wrong, let's say that somewhere in the earlier stages of your Klondike bar crafting here, your battery machine goes down and that PLC goes down, and the PLC is like, hey, we can't do anymore, right? This is actually good because a lot of industrial systems, really the goal of a lot of it is to maintain the mission, which whatever that mission is. In this case, it's making Klondike bars. That's in an OT network, ICS infrastructure. That mission is more important than the data, right? That's more important than protecting data. It's more important than safeguarding your bank or Netflix or Ashley Madison credentials. So this is good because this means that everything else goes down. You're not wasting time and energy trying to. If these things run, they could be mixing things that aren't there. They can break down. They can waste and spend energy that you don't want to spend, right? Costs a lot of money. So next thing we're going to be looking at is a distributed control system, this time using autonomous controllers. An autonomous controller, it's similar to a PLC, except for the fact that it is very siloed in its operation, meaning that it controls that one process that it's in charge of, and it doesn't talk to the thing next to it because the networking of these controllers hasn't gotten there, and these things don't get updated, right? They don't get updated for long times. So typically these kinds of systems are set up to run for 10 to 12 years straight. So any kind of update cycles are not like they are in IT. So you do have distributed control systems, which you have siloed controllers like this, in which if a controller goes down and a process goes down, the rest of the stuff keeps going, which can expend energy and can end up breaking stuff down the line. So digging into what is a PLC, we're going to deep dive in that now a little bit more. So a PLC, typically you'd have PLC setup is to set it up on a rack, and it's modular, so you can just kind of add them, take them off. So you start off with a PLC device here. I'm just using Siemens because they have the best sprites I can use. It's not a product endorsement. Then we're adding processing power. So when you're adding processing power, you are then allowing the PLC to do a little bit more. It's not like stopping a computer, taking it apart, adding RAM into it. Then you typically have this in a cabinet, and the cabinet would shut. There would be a lock on the door of the cabinet holding the thousands and thousands of dollars worth of equipment. Or what you can do is you can have this right here is have a RTU or remote telemetrics unit, which basically would sit, this could sit a number of places, but just to kind of show for this example, it's managing it. It's collecting metrics from a device and sending it home there. That's typically going to be over some kind of data cable. So programming languages for PLCs, we have a lot of them. When these industrial technologies, these technologies allowed us to engage in automation. When they first started coming out, there's one vendor, then there's a couple of vendors, then there's like, well, we're just going to make our own languages, our own protocols, and use our own programming languages for these. So eventually it got to a point where there was a regulation put into place, ICS 61131-3, that says you need to use one of these 5. And so we have ladder logic or ladder diagrams, which are kind of schematic for anything logical and physical. And you have sequential function charts, which are kind of a graphical way of programming. Then we have the function block diagrams, which describe functions for I/O, and they're set up in a way that you can make these tasks repeatable. So when you make one function block, you can kind of store that and pull that out, use it later, kind of thing. It's kind of like almost like block programming, if anybody's done things like Scratch or something. And then structured text is more something similar to like Visual Basic or C, something a bit more written using logic that you can understand there. Then instruction list, which is kind of, it uses mnemonic codes for instructions, and it's a text-based language that resembles assembly, if anybody's ever worked in assembly before. So next, multiple protocols used. So a few seconds ago, I said that there's lots of vendors, right? So vendors will typically have their own protocols, or some will be shared. Modbus is one of the most prolific out there. If you were to go to Shodan, look for industrial control system technology, most of what you would see is Modbus. And then there's Siemens S7 proprietary protocol, which is from Siemens. DNP3, Niagara Fox. I'm not going to get into each of these, but this just kind of paints a picture of how many communication protocols are out there, which makes attacking industrial stuff easy and hard at the same time, depending on what your mission set is. And function codes define capabilities of a PLC. So a couple function codes I'll really be talking about from an external security testing standpoint will be holding register addresses, which are just 16-bit words that contain numbers, presets, values, any kind of math, right? Then our coils is what stores the ladder logic. And so if you can read them, they're just going to be ones and zeros, right? But we do know that if we flip the bits, then bad things are going to happen. You don't have to know what, you just know that bad things will happen. So getting into SCADA, this is a lot of bullet points here. So collection, really all you have to realize is that a collection of both software and hardware components that allows supervision and control of plants, both locally and remotely. The remotely part is kind of in contention because there's a lot of schools of thought that say that we should not be controlling factory assets remotely, which is yes and no, because you'd have to make sure that the communications is really, really secure, which is a specialty of mine for IT/OT convergence. It's something I've done a lot of research on and talked on a lot. So really your SCADA system is where all the data would sit, where all the data goes. It's if you wanted to pipe your data up, you would most likely pipe it up from the SCADA system because you can get logs and data and metrics that you can actually send up. So I don't want to read all the bullet points here, but hopefully some reading was being done while I was talking there. Okay, so when you involve a SCADA device inside of an OT network that houses industrial control systems in any way. Your SCADA would typically be at the top of that hierarchy. This kind of goes back similar to that Purdue model that I had showed you before, the layers of hierarchy there. So you can do something like this as far as architecture is concerned, just to kind of build a simple idea. You can build something like this where you have a PLC that controls the PLCs under the SCADA. Or you can have something like this where you have the SCADA and there's the PLC under that controls the PLCs, that controls the PLCs, that controls the process. Or you can do something like this, which these are all notional. I don't think you should really do any of these. I'm just trying to tell you what you can do if you wanted to. But yeah, no, that's not good. Yeah, so story time. Telling the story of the first SCADA network test that I ever did that actually kind of careened me into this path. So, a few years back, I was contacted by some people that represent a major metropolitan city, and they wanted me to do, they wanted me to test their metropolitan transportation infrastructure, right? And because I was a pen tester, the best pen tester who uses Parrot, not Kelly, I said yes, and we shook hands, and then I was getting ready to make all this bread and then party. But when I actually did the test, you know, things kind of went like that, right? So I didn't know what the hell I was getting myself into. So I'm going to skip the showing of the report because the takeaways are the next slide here. We started a bit late, so I'm not going to try and hold up the timeline. So basically, there was a single process that I was testing at that point. I had found out that you can query the PLC, ask it like, hey, what can you do? Now, mind you, this is a single PLC that's supposed to be managing a piece of automated transportation, something that people get in and then it stops and it goes and it stops and drops off people, picks them up. And the PLC that was managing this interaction, that was, you can ask it, hey, what do you do? And it says, oh, I do these things. Take a look at what I'm holding, and then here's my logic. And so it was susceptible to a few things. Coil value injection, which all that is you're gaining access to a PLC and then flipping the bits from 0 to 1 and 1 to 0. And then function code enumeration, you can ask it what it does, and it'll tell you what it does. And then you can do the holding register address value injection, which I'm going to have an example of that coming up quite soon. And then denial of service. So sending these PLCs, they're kind of rigid and a little fragile in some cases, right? So basically what happens is if a PLC is expecting Modbus communication to come into it, or DNP3 or S7 or whatever, then if you're sending it things that aren't that, then it will just go, oh crap, what am I doing, right? And so you have to reset it. And that happened during the pen test. So yeah, it would stress it out, and I wasn't really trying to do that at first. I was trying to do it like a light fuzz to kind of see what inputs it would accept, and it did that. I'm like, well, I may as well just run HPing and see if I can, validate that DOS attack would work on it, and it did. Yeah, so I'll get into the demo really quick. It's going to kind of enumerate some of the things that I had just talked about. So, demo video here. When I was doing that pen test was kind of like the start of a lot of things for me, because when I realized like how cool this shit actually is. So I ran into an issue where I had to query. I was using a socket tool called, I think it was a Python. No, it was a Perl. It was called MBTGet. And I had to query blocks of the register, the holding register, to kind of say, hey, all right, now that I know that you can tell me what's on there, just dump it, right? And so there's an issue with that particular Perl tool. It was one of the best ones out there, though, still given that situation. So I ended up having to write a Python module that would just, I would say, hey, just do this whole block, and then iterate it and, put it into a list. And then once you're done with everything, just print everything out. And so I ended up turning that into a tool called Rapid Fire because I ended up doing more of these tests. And so what Rapid Fire is it's a Python wrapper that I now extended for MQTT, for peer-to-peer IoT devices, and then ATG, or automated tank gauges. So like a lot of gas stations in the area have pumps that you expose to the internet for a couple reasons. One, there are analytics platforms that can integrate with them, much like they could on a Modbus PLC or something else. Or two, they just want to be able to do remote diagnostics and see how much gas they have from the comfort of their home or the coffee shop or the toilet or something. So I'm going to play this really quick. So the tool that I just told you about, Rapid Fire, that's this whole left panel right here. And on the top right, I know this is a little, you know what? There's a good reason why you're not seeing it. Can we all sort of see it in the back? Okay, so it's not mission critical that you read every single thing on there, but I'm going to describe what's going on as it's happening. So here, the top right is those are the holding register address values for this this target PLC, and then the bottom right are the I have a laser pointer. Top right is the holding register address values that I'm loading in a watch window. That I also ran a watch to query the same kind of deal, but on the coils. So you just see ones and zeros. Up here, you see this. Now, from the outside looking in, you have no idea what that is, right? The only way that you know what that is if you have inside knowledge of the kind of secret sauce that those engineers are putting on those PLCs. But to us, it's just gibberish garbage. So I'm going to run this here. So the first thing we do is we're using the tool to identify which functions are enabled on our target PLC. And so we're just targeting it. That's all we're doing. And right here we basically just ask the PLC, hey man, what can you do? Tell me about yourself. Tell me all that secret stuff you can do. And so we see right here that it tells us we can read multiple holding register, so which is what we're doing right here, right? But we're just for the purpose of the demo video. So we just identified one of the functions of this PLC, this target PLC, is that we can read the multiple holding register addresses, which we can see right here. We're reading 1 through 22, and there's a lot more than 22. But 22 is the magic number that I can fit on the screen. So next, let's let that go for a little bit. You can also read the coils there. That's what I'm highlighting here. You read the coils and highlighting those here to kind of make that connection. All right, so we stop it, and then we're gonna break it because that's what you do when you realize you can do something. So what we're doing here is we're targeting the PLC, which is sitting on a test bed somewhere. So what we're doing is we are saying, hey, registers 1 through 22, we're going to rewrite them with a single numerical value, and you can see they all change right here, right? So imagine that is imagine that PLC is managing something in like a water treatment facility, and then all of a sudden, bam, everyone in Raleigh's poisoned because you didn't secure your shit. So not exactly like a FUD scenario, but just to kind of show what can be done. And we can do the same thing for coils. It's going to look like the same thing, pretty much. So we're saying, hey, gather these coils together, and we're going to just rewrite them with all 1. And as you can see right here, they're all going to get rewritten with 1. And so if you can get an access to a Modbus PLC, that's how you break it. Just a simple, kind of a simple thing. But yeah, I mean, that's, yeah, so quick review. We went over kind of the basics of industrial control system network, how the architecture is supposed to look, a couple of the weaknesses about it, a couple of the weaknesses in PLCs that are exposed. Got to tell a quick story about my first SCADA, or my first OT technology pen test. Does anybody have any questions? Well, I do. I have the repo for rapid fire. You can take a picture of that if you want to. That would be the part where I do encourage it, because I do like hearing feedback, like, hey, this is informative. Hey, you suck. I'm open to whatever. I like talking to people about this stuff, which is why I do this. The rapid fire is, yeah, it's on GitLab. There's more dependency-based setup docs that I'm putting on there, but yeah, okay.
Did you plug in like using a Linux box and you wrote this script and on a Linux box and just plug it on the network and then attach the PLCs?
Yeah, so if you're doing that for this particular test I did for the video, yeah, but oftentimes it might be something that's exposed to the internet. If it's exposed to the internet, it's going to look the same. The only thing is that you're doing this attack over WAN versus LAN. So.
Yeah, it doesn't matter. I mean,
yeah.
They expose themselves on the net.
Mm-hmm.
But your attack tools pretty much just use a Linux OS for that.
Yeah. Yeah, I use Parent OS for that. And even then, it wasn't any specific security tools. It was just me figuring out what I need to communicate to the PLC in its own language. And then I was able to quickly write a Python module to just repeat those attacks, or repeat that dialogue, I guess. Not technically attacks until I decided to attack it. But yeah, that was pretty much it, yeah. You can do it with a Windows box too if you wanted to. I mean, Python works on Windows, right? So, but yeah. Any other questions? Yes. Yes. Okay, so the question is, do autonomous controllers phone home to something or speak to something so there's some kind of synchronous time? Yeah. So that is okay, so I'll give you a two-part answer. First part, because that's going to look different based on the environment. So like older environments probably didn't have that. When making old environments, the presence of thought to do that might not have been there. So it becomes a manual process. You can still sync up controllers to some kind of other management hierarchy because none of this is static or as rigid as it sounds. This is just kind of the intro, right? However, yeah, that's does that answer your question or?
It does. So I think my question has more to do with coordinating between the systems. So, for example, the refrigerator here is going to start refrigerating as soon as it receives chocolate and ice cream from the mixer. And how does it know to do that? Say, okay, I'm going to do this a certain amount of time after I power on. Does it say, hey, I have this, I'm going to do this at 12 o'clock every day? How does that work?
Yeah, and so from my understanding with autonomous controllers, because I will say most of the testing that in the hands-on I've done are newer PLCs that have this kind of intercommunication going on, or that can have that going on. But from my understanding, the autonomous controllers are programmed at the controller level specifically. So that takes kind of taking a step back and realizing what's going to have to happen at what time, which is why it's something that I don't recommend, but there might be situations where the mission set allows it. That's the best I can say on that. Yeah, no problem. Anybody else have other questions regarding industrial control systems or any of my other interests? Anime, Xbox, yes, anime, right? No.
I've been writing Kali, Linux, and Parrot, and different VMs trying to compare the two. Why do you want Parrot?
Oh yeah, so I was never a fan of the Linux GNOME UI. That and doing a lot of stuff in Cali required a root account at the time. I don't know if it's changed. I haven't used Cali in like 4 years.
Some of it has changed.
Okay.
And they also have the options of different GUIs and everything on it.
Okay.
Cali just updated the last month.
Yeah, it wasn't. So the feeling, for me, it wasn't as intuitive. And also, I don't know if Cali has this now, but at the time, Parrot had like, how do I say, like incognito modes where everything that you do can get piped through Tor, or it can get piped through whatever destination you set up in proxy chains to do. That's kind of a big reason. Parrot seemed more intuitive to me, and some of the options were a little bit easier to employ, I guess. Yeah, which probably sounds like a bogus answer to somebody who's like really versed in Cali first, but I mean, that's preference, right? Any other questions, comments, concerns? Okay, cool. Thank you.